So what about eggs? Okay, so I've taken this figure and lots of other figures from your textbook. Um, Cooking eggs again is going from a dissolved proteins that are happy and folded in their native states, doing their jobs, to this large scale, long range protein gel. Again, heat causes the egg proteins to unfold. They form a dense network. This is referred to denaturation and aggregation. Um, However, we want to be careful when we're cooking with protein that we make, and we want to, again, we're trying to achieve a particular goal, a particular texture perhaps, and so a little bit of heat can be a good thing, and we form a nice, firm network. But if we cook too hot and too high, then those proteins can aggregate with each other more and more and more frequently, and this will eliminate water, which is an important component of the network. We can squeeze out that water and we get a dense rubbery network. So that might be a texture that we want to achieve in some cases and not in others. So we have to remember the effects of prolonged cooking at high temperature on our protein gels. Something that I mentioned previously, and I think in another lecture, is the difference in unfolding temperatures of proteins. So here we're looking at different components the of the egg. Here, yolk, we're referring to it as an aggregate set of molecules, but there are yolk proteins that unfold at 158 degrees. Ovotransferrin is a molecule that begins to unfold and aggregate at 145 degrees. Remember, ovotransferrin is a relatively small component of the egg white, but still at 145 degrees we should expect to start unfolding the white, whereas the egg yolk we should expect to remain more liquid at that low temperature. And then once we start to increase the temperature, the ovalbumin, which remember is something like 50% of the protein component of the egg white, unfolds, and we can get a much denser and thicker egg white network. Now, okay, what is this unfolding? So here's a molecular dynamics simulation of a protein. We don't care so much about what its structure is, but we see that when we apply heat, different pieces of the molecule begin to unfold, lose their structure, right? Maybe exposing themselves to the solution in ways that they otherwise would not. Reminding you that when that happens, those exposed segments are free to interact with other proteins in solution, forming again this long range network. Okay, so I did an experiment here looking at eggs cooked at different temperatures, 145, 155, 165 degrees Fahrenheit. And we see, remember, ovotransferrin beginning to solidify at 145 degrees, the yolks far from their coagulation temperature. And then at 155, we see that we've got a pretty firm white here, but the yolk is still quite liquid. And then at 165, everything begins to solidify, and we see that the yolk and the white have both become solid. So, reminding you that the composition of the ingredient or the item determines its chemical properties. Okay, your experiment that you've been working on, or will start working on this week at home, involves egg formation and egg foam formation. Excuse me. And egg foam formation is a great example of protein unfolding and aggregation. So that's why we focus on it so much with eggs. So here again is a nice picture that you can stare at while I talk to you about egg foams. Whipping introduces tiny air bubbles into a liquid. That's obvious. Mechanical stresses denature some proteins, as I said earlier. Also, exposing proteins that are dissolved in water to an air-water interface unfolds them. And so these unfolded proteins form networks of aggregation around those air bubbles. So what we see is the stabilization of those air bubbles with unfolded protein, as well as the stabilization of a long-range network by the unfolded proteins forming around those bubbles. As we heat the mixture, we can unfold more proteins, making that network yet denser. And in many cases, we'll see that the foams that we make, we will cook those, and they do stabilize somewhat when we cook them. So that's all there is to egg formation. We increase the volume of the solution by introducing small air bubbles. The smaller, the more, the better. And we stabilize those bubbles, which would otherwise just pop again and disappear. We stabilize those by unfolding proteins and forming dense networks around them. Okay, now some complications involving sulfur. First of all, by the way, I should say that a lot of the eggy smell of eggs derives from the formation of hydrogen sulfide. Many proteins include sulfur atoms, and when we unfold and expose those sulfur atoms to air, they are quite reactive, and we release hydrogen sulfide, and that has a strong aroma. So overcooked eggs will frequently smell strongly of hydrogen sulfide. But the sulfur also plays an important role in egg foam stabilization and destabilization. So again, forming a network of aggregated proteins that's too dense results in a loss of water, and the effect of your foam is that it collapses and has a sort of a grainy texture. So the water is important for a nice structure in our foam. Well, the sulfur atoms are, as I said, pretty reactive, and they can form something called intermolecular disulfide bonds. What does that mean? That means that a sulfur attached to one molecule of unfolded protein can form a physical covalent bond to a sulfur atom on another chain. So that's what intermolecular is, as opposed to intramolecular. So that strengthens the network, right? That might be a good thing, except for what I told you before about the too dense of a network causes our foams to actually collapse. So those disulfide bonds that form are actually something that we want to avoid. And we have a few ways of avoiding them. And that's what our experiment is all about this week. So first of all, we can use copper, and your text talks a lot about the use of copper bowls in whipping up egg foams as a source of the copper. If you come by my office, I'll give you some copper chloride to try yourself. The key here is that copper reacts with the sulfurs that are exposed in those unfolded egg white proteins and prevents them from forming these intermolecular disulfide bonds. So we avoid the formation of a too dense network, which is a little bit counterintuitive, right? The foam is stabilized by prevention of too dense of an aggregation network forming. So weak organic acids do the same thing. Well, acids can unfold proteins. That's part of the process, but they also protonate those sulfurs, right? So they prevent this protonation prevents the disulfide bond formation once again. So twofold effect going on with weak acids. Now, for the chemists in the audience, let me say I've given you 3 different kinds of acid to use in your experiment. Why don't you find out the strength of those acids, the strength as measured as the pKa of those acids, relative to what you think the pKa of the sulfur is. So at what pH does the sulfur get protonated, and how does that play into the ionization of the weak organic acids that you're studying? So you can use that as a way of thinking about how different weak organic acids affect the stability of your egg foams. So turning from foams, let's think about eggs interacting with other ingredients. And it's mostly dilution that's going on here. So our open mesh of denatured proteins gets more open and therefore more delicate perhaps. So here again is a McGee picture. We've got egg proteins. Now we're associating those egg proteins with a fat globule. We're going to talk about milk next week, so stay tuned. But in any case, the milk fat globules form an emulsion with water, and those egg proteins will see that oily surface and denature and form again this complicated network surrounding and linking those fat globules, similar to what we see with the air bubbles in a foam. So, but milk, fat, and sugar all dilute the heat unfolded protein so the gel becomes more diffuse, and so we get again a gel network that's much more um, light and much more delicate than what we see in a foam. The examples that are discussed in your text are custards and flans. In this case, we have a dilute cream mixture that we cook to form this very delicate network. And if you've had custards, then you'll know that while they are a very they do have a very light texture. It's also a very delicate texture. At the extreme of dilution, there's eggnog. So there's very little egg relative to the liquid component, and the proteins are also usually not cooked and therefore not completely unfolded. And what that means is that they can't form a long-range network that results in a gel. Instead, they just increase the viscosity of the liquid. So you've got everything on the one hand from a hard-boiled egg, which has this dense network of unfolded protein, to egg white foams that has a much more light and airy network, to increasing amounts of liquid mixed in with your egg whites, and you get lighter and more delicate and more diffuse unfolded protein networks. Well, let's think about egg dishes. So there's a variety of ways to cook eggs. On their own. So just the egg itself. So we can cook the egg in its shell or cook the egg out of its shell, and we're familiar with all of these probably. I myself do not eat soft-boiled eggs and have no plan on eating a soft-boiled egg. But in a hard-boiled egg, we simmer these at. Note that these temperatures are below boiling. So this is important again for if you're interested in maintaining a pleasant consistency in your hard-boiled egg whites. Simmer below a rolling boil for 10 to 15 minutes. And some people like a firmer texture and a more developed egg flavor. And if you like that, then you'll cook it at higher temperatures and for longer times. And again, this results in the development of hydrogen sulfide. Now, if you cook for too long, what you'll see is that hydrogen sulfide can react with iron, and that's while harmless, not necessarily the most aesthetic coloration for your eggs. Unless you like Dr. Seuss, you'll get greenish yolks with this iron sulfide formation. Out of the shell, there's a variety of ways of cooking eggs out of the shell. Baked eggs, you can place your egg crack your egg into a mold in the oven, but then you'll probably gonna want to use a water bath. The water bath prevents overcooking. So we maintain the temperature even though we're in an oven, we maintain the temperatures at levels that just cause those proteins to begin to unfold. Relatively infrequently used cooking method in the United States. Poached eggs are something that certain people, for example, those of us that like eggs Benedict, crack the egg into hot water, and we'll see the egg white cook nicely around a nice soft yolk. Now, here again is where those grade AA eggs are very important, again because of the density and the cohesion of the egg white. As you drop that egg white into the water, you don't want it to diffuse, you want it to stay into a nice intact whole. Something that's more familiar to me personally are fried eggs, and we can use high temperatures. As I said, high temperatures might result in a denser, tougher egg white consistency, but we get some tastiness coming from actually burning the egg and forming brown, crispy surfaces. And we'll talk a lot about browning later. But if you're interested, skip ahead in your text to Maillard reactions for browning. Scrambled eggs. Your text dedicates a lot of energy to thinking about the proper way to cook scrambled eggs. Part of it is to cook them slowly, and this again keeps your network open and retains a lot of water. Omelets are very fast cooked on the exterior, and then you close that exterior up and cook the interior more gently. Now, these are a bunch of ways of cooking eggs on their own, especially for these no-shell varieties. It's easy when you watch cooking shows to learn about doing things the proper way and following the recipe exactly. Much more important is to think about the experience that you want. For myself, I like to scramble my eggs by not disturbing them very much, and turning them only once or turning them really only once. Whereas some people will really scramble those eggs continuously. You get a very different texture, and maybe that's the texture that you like. Let's watch a cooking show. Here's Julia.